Hello all. So we will continue with the design of our image processing IP. So in the previous tutorial I have shown how to design our line buffer. So in this tutorial we are going to design the module which will be doing the multiplication and summation operation. Okay, so basically this module will get the pixels and it will also get the kernel, and it will basically multiply the pixels with the corresponding kernel values and add them together. Now, what kind of kernel we are going to use? Yeah, there are different kind of kernel depending upon what you want to do. So in Wikipedia, there is a good illustration of different kind of kernels. We have the identity kernel, which does nothing. So the output image will exactly look like the input image. Then there are kernels for detecting the edges. We will discuss it later. Then kernel for sharpening, and there is a kernel for doing the blur operation. So we are going to try this out. Okay, so this is our 3 by 3 kernel, and you will multiply pixels with 1, so there won't be any change in the pixel value. But what you are basically doing is, for every pixel you are adding that pixel value with all his neighbors, all his 8 neighbors, and dividing the entire result by 9 to get the output pixel value. So effectively you are finding the average of one pixel and all his neighbors as the output pixel value. So this will look like a blurred image. Okay, so this is also called an averaging filter also, because you are taking the average of the pixel and its neighbors. Or sometimes we call it as a smoothing kernel also, because you are getting a smooth image as the output. Okay, so this is the kernel we are going to use. Now I will just show the effect through MATLAB also, so that you can see what is the expected result. So we will be, when we test the image, we'll be using again Lena. So let's see what is the expected output. So let's try it in MATLAB and see how it should look like. So I'm reading the image. Now let me define my kernel here. So we are going to use this kernel. Okay, 111111111. So 1111111. It's a 3 by 3 matrix. Now we will do a 2D convolution between this kernel and the image. So and divide each pixel by 9. Okay, so we'll say output equal to 2D convolution between the kernel and image, and you divide every value by 9. Okay, so this is the output. So if you notice, my input size is 512 by 512, but O size is 514 by 414. This is because of the way how MATLAB takes care of the edge pixels. So he's actually adding additional pixels to the edges. So instead of reducing the image size like I discussed last tutorial, in MATLAB it's actually increasing it by 2 pixels. Okay, 512 by 512 became 514 by 514. Now the data type is double because we are dividing by 9. Okay, so in order to display it, I need to convert it into 8-bit. So we'll say like O equal to, again, typecast of 8, and let's see how it looks like. So okay, I'm sure this is our original figure, and okay, so this is the figure after this blur operation. So if you compare these two, you will see like there is a smoothing effect. The edges are no longer sharp, especially on the cap. You can see all these ridges, they are smoothened out. Okay, and here also. So same operation we are going to try using the FPGA. Here, if you notice closely, you will see the pixels on the edges, they are all black. Okay, because it's a 514 by 514. So there are two additional rows, one at the top and bottom, and two columns, one on the left and the right. Okay, so this is what we are trying to do using FPGA also. So this is the expected output. Okay, so we assume the module which is instantiating the line buffers and these multiplexers, we will design them later. My current assumption is these output from the multiplexers, they are already available to me. And remember, these multiplexers, they are coming from the line buffer, and at one time you are reading 3 pixels from line buffer. Okay, so the size of this wires, it is 24 bits per line buffer. Like that, we have 3 line buffer. Okay, so that's the assumption how data is going to come, and we are going to get data from all 3 line buffers in parallel. Okay, so we have 3 line buffer, each one giving 24 bits. So based on that assumption, we can start coding. Okay, so let's call this module as, it's actually doing only multiply and accumulation operation only. It's not exactly doing the convolution, but still let's call it conv to indicate it's doing convolution. Okay, so we need input, we have clock, and we have data coming from the line buffer. Okay, so as I mentioned before, we had 24 pixel and 3 line buffer, and like previous tutorial, as I mentioned, you cannot declare it 2-dimension. You have to flatten it and declare it as a single 1-dimensional array. Okay, so in total we have 24 times 3, 72 pixels coming. So I'll just call it 71 down to 0. Let's call it like I pixel data. Now there should be again some kind of indication that this data is a valid data, like our axis stream again. So we have I pixel data valid. Now same way, this module will give the convoluted output, or basically multiplied and accumulated output, so which will go as the output pixel value. Okay, so he will basically multiply all of them and add them together. So the output result, that should be 8-bit. Okay, after you do it, which will be going as the output pixel value. So 7 down to 0. Let's call it as O convol data. And again we need some signal to say this is a valid data. Okay, O convol data valid. Fine, that's the port declaration. Now we need to declare the kernel. Okay, so kernel, again, either you can declare it as a 2-dimensional array because you are now inside the module, or you can declare it as a 1-dimensional array by flattening it. So let's declare it as 2-dimensional array. Reg, what should be the width, what should be the depth? So we need 9 values each for each location here. So we have 9, and each one of them, what should be the width, depends upon what value the kernel is going to store. So in this case it is going to store all 1, so 1 bit is enough, but maybe later we want to try maybe Gaussian blur and all. So we just want to change the kernel value, so let's again declare it 8-bit wide. I'm just choosing 8-bit. Okay, and kernel, but the depth is 9. Okay, so I'm modeling it as a 2-dimensional array. If you wish, again you can combine them together and declare it as a 1-dimensional array, but this will make things easier. Okay, so we have our kernel now. Now let's initialize the value in the kernel. Since I'm going to use a constant kernel, I can use the init block to initialize the values of the kernel. Okay, so let's say kernel 0 equal to 0. You can either like this, or let's use a for loop. Okay, for I equal to 0, I less than, we have till, okay, I equal to I plus 1. Since we have same values, I can just write like this. Kernel of I is 1. Okay, so that will store all the values. We need to declare I integer I. Now this for loop, again let me repeat, this is not like software programming. It's not like there will be some hardware which implements the for loop. What happens is when Vivado runs, he will analyze your code and he will unroll this for loop. Okay, and it will be equivalent to writing kernel 0 equal to 1, kernel 1 equal to 1, so on and so forth. Okay, so now let's do the multiplication. Okay, so let's write it sequentially for such a clock, and again let me use the for loop to do it multiplication because it's 1 to 1 multiplication. Okay, I equal to 0, I less than 9, I equal to I plus 1. What we want to do, we want to multiply the kernel ith value with the corresponding value coming from here. Okay, so 0 to 7 here should be multiplied with the kernel of 0. 8 to 15 should be multiplied with kernel of 1, so on and so forth. So either you can unroll it and write it. If you are writing it in the shortcut format, again remember the syntax. So you need to write it something like this. I times what is the width plus colon 8. Okay, so initially I will be 0. So this will be like 0, starting index 0, width is 8. So it represents 0 to 7, so on and so forth. So this I should be stored somewhere. So let's declare some place. Let's call it mult data or something. That's where I'm going to store the result of this multiplication. So again, that is 9. Depth, width depends upon the width of the operands. So ideally this is 8-bit and this is also 8-bit for each multiplication. So at least theoretically this can be 16-bit wide, but currently practically kernel is 1, so 8 bits are enough. But again, let's put it like 16-bit because later maybe we'll change the kernel values. Okay, so mult data of I is something like this. Okay, now if you notice, I am doing one level of pipelining between my input data and the multiplication. Okay, so we'll come back to that later, I guess, for clarification. Okay, so we multiplied it. Next is we need to add it. Okay, now addition. Okay, let me try to write first and explain. I clock. Again, if you are using for loop, it may look something like that. For I equal to 0, I less than 9, I equal to I plus 1, begin end. Okay, we need to add them together. So let's say like some data or something. This is where I'm going to store it. How do you add it? Some data plus, okay, mult data of I, and maybe some data we need to initialize to 0. Okay, so this is how we exactly write it in software also. Okay, so here also it looks fine, but if you do simulation, you will find like this won't be working. Okay, because how this non-blocking operation works is slightly different. Again, if it depends upon your previous experience in Verilog, whether you really understand it or not. So when you are using this non-blocking statement, that means the value on the right hand side should be propagated to the left hand during the clock edge. Okay, so based on that, if you write like this, when you come to this loop statement, the sum data won't be initialized to 0 because it is going to get this data only on the next positive edge of the clock. Okay, so when you do this, some data is supposed to have still its previous value, and you are asking to do this entire addition on a single clock edge. So he will implement it in parallel, but when you do simulation, most probably some data will be X at the beginning, his previous value. And next clock, when you do it, some data will be having, I don't know, again X, because you are adding X with something, unknown with something. So you will find like in simulation, it really doesn't work, but practically it might work. Okay, so that is one place where modeling and real stuff are different. Okay, so to avoid it, what you can do is, if you write like this will work. Okay, this is blocking assignment. That means sum should be initialized to 0 before coming to the for loop for simulation purpose. During implementation, the implementation hardware might be exactly same as before. But the problem with this one is, if you write this statement, this means some data should be changed immediately. Okay, so previously, if you remember, I guess I mentioned, when you do simulation, even if you see like data is changing on the clock edge, actually it is changing slightly after the clock edge. We'll say like some delta time after the clock edge, t plus delta t. But if you write like this, that is not the case. Some data is changing with the clock edge itself. So if you look at the value on the clock edge, it will have this new value. So again, there will be some simulation mismatch. There will be some mismatch between simulation and the real implementation. So to avoid all these things, what we can do is, again, you may feel like, okay, so if I write like this should be solving the problem, because some data should be immediately initialized, but this some data should come only after the clock edge. Again, the problem is for Vivado, you cannot mix blocking and non-blocking assignment statement inside the same always block. Okay, so that's a restriction in Vivado. So if you do like that in simulation, everything works as expected. Maybe implementation should be also working perfectly, but Vivado, he won't let you synthesize it. He will be able to simulate it properly, but he won't let you synthesize it, saying you cannot mix blocking and non-blocking assignment statement. So to avoid all these things, what we will do is, so practically what does it mean? So we need parallel adders. Okay, we need 8 adders to add these 9 variables together, and on the clock edge it should go out. Okay, so that adder circuit, it is actually a combination circuit, and I can model the combination circuit like this. So this represents a pure combination circuit. Okay, makes sense. And on the next clock, I will assign this sum data to something. Okay, so let's call it some, this is some intermediate sum operation, sum data int, and here I will say like, okay, sum data is sum data int. So this should solve the problem. This is also modeling exactly what we wrote before, but when you write this style, there will be matching between simulation as well as the real implementation. Now you need to declare them. They are inside always. So although it is a combination circuit, since it's inside always, it should be declared as reg type. Now what should be the width? Again, ideally this is mul data. You can take the worst case scenario and find out what should be the width. Here our mul data is 16-bit. So let me declare this also as 16-bit. Okay, so some data int is this one, and some data, let's make that also 16-bit. 16-bit. Okay, ideally what we should do is we should find out what will be the maximum value of mul data. So in the worst case, what will be the maximum value coming to some data based on that we need to declare the width. But again, I know like the kernel value is only 1. So in the worst case, what will be the value? You have 255. We have 255 as 1 pixel value. You are multiplying with 1, so it is 255, and you are adding 9 of them. So this is the worst case value, and to store this I need only 12 bits. But let's again keep 15 bits in case, 16 bit in case we change the kernel in the future. Okay, so that's done. Now last part. So you need to multiply, add them together, and finally it should be divided by 9. That represents the single output pixel value. So again we can write it in another always block. Why I'm writing it in different always? So you can model this entire thing happening in single clock cycle. Okay, so you will have a big combinational circuit which is doing the multiplication and addition and this division, everything together in the single clock cycle. You can do it, but that will make a big combinational circuit again, which can affect your timing performance. That's why we are adding pipelines in between. So this is one level of pipelining. You can see multiplication, one level of pipelining. Then we are doing this addition, this one that is happening in parallel. That is another level of pipelining. And finally, next level of pipelining, which will be division by 9. A good thing is previously signings tools like ISE, it never supported direct division operation if the denominator is not a power of 2, but currently Vivado it is supporting division by numbers which are not power of 2. So that is a good thing. So we can directly do some data divided by 9. Previously, because 9 is not a power of 2, we were forced to instantiate some IP core for doing this kind of division. But now they support it. So this should be reg type because it's inside always block. Okay, so that's the logic. Now the only thing missing is O control data valid. Now how do you find this one? You just find out how many pipelines are there between your input and output, and you add equal number of pipeline to this signal also. Okay, so where is our first pipelining? First pipelining is coming here when you're multiplying. So let's call it mult data valid is ipixel data valid. Okay, so next one is this one. So here let's call some data valid is our mult data valid, and here we have the division, and here we can say, so this is also reg control data valid is some data valid. Okay, so we are just pipelining the data valid same number as the pipelines for the actual data path. Okay, so that's it. So we need to declare all of them. Mult data valid, control data valid. And some data valid. Okay, so that completes the design of this module. If you wish, you can go ahead and simulate and see, but I'm pretty confident this will work because there is not much logic. Okay, one thing I would like to add here is when you are dividing by 9, you may not get an integer, right? I don't think in most cases you will be getting an integer. So in Vivado, if you do like this, he will build a circuit which will take only the integer part and it will assign to O control data. Okay. Now again, this is a 16-bit data, and this is an 8-bit data. So what happens is he will divide and he will take only the integer part, and the lower 8 bits of that integer will be going as the output. So when I say like he will take it and all, what I mean is the circuit implemented by Vivado is something like that. So it takes this data and it divides by 9, and the output will have only the integer part, and the lower 8 bits of that integer part will be going out as the kernel data. Okay, so that's it. So next part in next video. Thank you.